And then, of course, no good deed goes unpunished. I'd like to.
Nobody what?
No good deed goes unpunished. So, I'd like to talk about monopoles on circle bundles over a compact Riemann surface. And they're obviously compact manifolds, so you have to put in some singularities. So I thought I'd begin by just recapitulating some work I did with Benoit Chelman a few years back, and then go on to discuss a more general case, which has some quite interesting geometry. So on circle bundles like this, you can think of, with the monopoles with the singularities, this sort of picture, where we'll be considering a sort of complex scattering along one particular direction. Is a sort of thing that was looked at more particularly by Kapustin in their geometric triangles work, and so sort of wondering what the self-Hecke transform, which propagating around a circle would give you. So the situation is we've got a monopole. So it's going to be a bundle, unitary. Across a circle minus a union of points, which I'll just sort of denote, I suppose, Ti and Ti. So it satisfies there's a connection on it. So connection. Whose curvature satisfies the Bogomolny equation. There we go, and I forgot Higgs field. Just section of the adjoint. So from these, this actually says that Fij is nabla k phi, and so from it you can extract, if you go to orientation chart, and as Nigel pointed out many years ago, this commutation relation, which essentially encodes two. This has three components to these equations. This is two of them. So what it tells you is that there's a d-bar operator that propagates in a third direction with not the unitary connection, but with this sort of complex shift.
So are you expecting any particular metric on this?
Just product. And I'll take the circumference of the circle.
And is it hyperbolic metric on the surface or a hyperbolic metric just arbitrary?
Yeah. Okay.
And notationally, so you're using T for the S1 direction and what
Yeah,
C
T
is the
is
fiber
the
direction?
S1, yeah. Okay, so maybe just recalling the Dirac monopole to U1 on R3 minus the origin, and we take a bundle, well, a line bundle basically, say of degree k, and you can write out connection matrices that are IKs are IK over 2, 1 plus, so in polar coordinates. So this is on the theta different from 0 patch, and a theta minus 1 with theta this is on the theta different than pi patch, and then phi is k to r. So this is the sort of model, the model widget, and it's written for arbitrary degree. So as I was saying, we want E to have some singularities on our situation. So we've got basically a bundle. That's a circle. And we've and some points, some coordinates, and so on, where the singularities are. And we're going to ask that the bundle be non-trivial on little spheres around these circles. So we fix some degrees. Some integers. N, where n is the length of the bundle. And you take E, it's a bundle on sigma cross S1 minus these points. And you want to consider solutions to the Bogomolny equation on these. So you want on solutions asymptotic to essentially the after conjugation, of course, to the so a diagonal embedding of the Dirac monopoles.
You're doing UN integral?
So making a unitary bundle. Now you'll have to, in some sense, generalize the equation. And so you, instead of having the Bogomolny equation, you have to sort of shift it a little bit. So you're taking, what I wanted, f equals or minus star number phi is, there's a constant that comes in. Okay, there's an I. A constant times the scalar form of the surface. So you lift it to, so there's a shift that comes in. And the reason, I'll just give it a second.
Or is that everywhere or near the direct monopoles or what's the?
Yeah. Asymptotic at
In the next line, what is this the fundamental equation?
This is the monopole equation, but shifted by this. And that's just like the Hermine-Einstein.
Tensor the identity, I guess.
Oh, sorry about that. Okay. So, so the reason you want to do this,
So that equals, oh sorry,
That's a minus.
that minus is a minus rather than equal, okay.
that's a minus and that's an equal. Okay. The reason is that these things have a degree which would just be the integral of sigma cross S1 of the curvature wedge dt. So basically what you're doing is just considering the curvature on each time. I might have missed a constant here. And this is just the average in t of the degree of course there's a trace, of the degree of p restricted to, well, average in t0 if you want, restricted to t equals to 0. Okay, so you take an average degree, and for a solution to these equations, you find that, actually it's just, sorry, it's equal to c times the volume of the surface over 2 pi then. And so this constant basically has to be there if you want solutions. And it's a bit, if you think of just U1 solutions, well, we'll come to this later and you'll see why. So basically the moral is C is linked, well, from this you can also
The
get that
Higgs
C is
field,
minus 2 pi, sorry?
sorry, the Higgs field doesn't contribute, so you're taking the trace of this equation, and the Higgs field.
I'm just taking yeah, you see that the nabla integrates out, and you just
What about
get
the
the,
singularities? It's not,
they don't cause any problem,
okay.
because you wedged it with the dt basically.
Mhm.
And you can try to sort of choosing an origin minus the sum over I, sum over j, ln j, tj, divided by t. Okay, so basically the moral is that C and the location of your singularities are and if you look at U1 solutions, basically, you can think of the, we'll see there's a sort of basic data, which is a scattering map. The zeros and poles of that are basically constrained by Apple's theorem. This is sort of the same thing, but in the circle direction. Okay, so what we do want to do is scattering. So you have your picture here. Monopole. And we'll just assume you've chosen t equals 0, so that none of these singular points aside. I should say that you do need that the sum of these tij is equal to 0. So that's, or these lij's rather. That's what these
What is the
are.
significance of the LIJs?
Hmm?
What is the significance of these weights?
Well, the lij's are basically, if you sum over j, remember this is diagonal thing, it's the degree of the bundle on a small sphere around the singularity. And for that reason, as you're going around the circle, you better come back to 0, come back to where you started with. So those things have to sum to 0.
And the LIJs are ordered or something?
You might as well, actually.
So, but I mean, it might clarify, in your original prototype, you called you have a K there, but if you called it L, it might be a little bit clearer that that's the.
Where was my K?
Yeah, you
Oh,
raise
okay,
here,
yeah.
you have the charge K,
So
oh,
you're
that
at
little
the
K,
K.
place that little K with.
There we go.
So the LIs are the Ks.
Yeah, the Li's are the K's. There's a small, the alphabet now has one letter less. I'll avoid stupid jokes. Okay, so you just take this, and if you're looking, for example, at, I don't know, t equals, or at whatever, 1 or t prime, you see basically that you've got one operator, which is this the surface operator along the surface here, so let's call it 0, 1, which gives you a complex vector bundle along the surface, because in one dimension, any d-bar operator is integrable. And the nabla t minus I phi allows you to move along. And basically, as long as you don't a singularity, sort of solving analytic minus I phi of s equals 0 for initial conditions here, and just moving it along to here, gives an isomorphism E0 to E prime for small t prime. And basically, it's just when you hit a singularity that you get something bad happens. If you do this for the Dirac, so the scattering for the Dirac, you just basically find, so you, through the origin, right, so here's the origin, I just sort of go along like that from the singularity to here, I basically get the K as my scattering map, where I've got, say, Z coordinate here, then a T coordinate here. Z is a complex coordinate. So what that means basically is, for this more general case, as I'm scattering through the singularity, in our case, the scattering gives, through a singularity, suppose a singularity is Z equals 0, so it'll give sort of G of Z diagonal Z to the Li, H of Z, where these two are invertible. And that's your.
So when you pass one of these punctures, the degree of the bundle jumps
It
by
bumps.
yeah. What the sum of the Li.
But that's, and this is in some sense shows that.
And that's why you have to have a consistency condition, so when you come back around.
When you come back to where you started with, you better come back to where you started with. So you go through this, and this, if you look, I mean, this is precisely the way meromorphic maps into a complex Lie group are sort of characterized. This is Iwahori. This is basically a co-character here, lies, positive or negative, and any meromorphic map can be sort of put into this form. So it's a sort of general Hecke transform.
What's it, the G of C's, they can be meromorphic?
No, these are invertible homomorphic. So you can make, in other words, you make all your singularity, whether zeros or poles, because these are supposed to be invertible maps, you can scatter back. You make all your zeros or poles, just live here, and the rest is a nice invertible homomorphic matrix.
The allies don't have to be positive, they can be negative.
Yeah.
Yeah.
And if they're going to sum to zero, you better allow it. Yeah. So that's the general picture. Now, well, once you're scattering, of course, you can scatter your way all around the circle. And you get E restricted to 0, 0, E restricted to 0, and this is now meromorphic with singularities. Let's call them poles, even though they're also zeros, possibly zeros at the PI. In other words, as you're going through this thing, it's only when you sort of hit one of these points as you're going through, because otherwise it's just nicely holomorphic all the way around. So you get the complex data that we're going to be looking at are these pairs P rho on the Riemann surface. Okay, and then the polar behavior of these things is actually specified by this data. Okay.
Curious about this
level where you're at the singularity, you're assigning some meaning, or this jump occurs afterwards?
It's the shadow of it's going through it. So your bundle, you go through it, and the structure of the bundle pops. You're getting something different. And then you go through it, and then it's going to pop here. You go through that one, and so on.
But I meant before and after. The comment was that the degree of the bundle jumps as it goes through.
Yeah, the degree has to, well, can jump, doesn't necessarily, because the sum of the LIJs at that point could be zero.
So what I'm asking is that jump in degree is occurring for all times strictly larger than, it's not at the time the jump occurs. That's what I'm trying to work out when the jump.
Well, it's at the time. Something bad is happening when you're exactly here, and then you go through.
So the state of the system at that time is what I'm trying to understand. Is that something that's
Metaphysics. I mean, you certainly have a parallel transport all the way to here, and then it just ceases to be at that point. The other thing is you can use the TI degree to define stability. So suppose that E prime is well, a subbundle of E is rho invariant. So it's a bit like the stability of the Higgs systems. You want it to be invariant under the action of this rho. Then it's going to have these integers too. Basically, this thing sort of nothing diagonalized as you go through these. And the stability, well, the slope of E prime is the T degree of the rank, and then E stable is the usual definition. If only slope of E prime, well, less than slope of E for all submodules E prime. So as for the Higgs constraint, this invariance is quite a strong constraint. For example, you can define a spectral curve for this thing. It's an endomorphism. And if the spectral curve is irreducible, then there are no invariant subobjects. So it's quite a, in some sense, sort of easy to test.
Sorry, how did you define the spectral curve?
I'll come to that.
Okay.
One question, does the rho determine the TIs in addition, or
No.
this is only?
No, they
defined to-
intervene. It's a bit like for parabolic structures. They just intervene in this picture for the stability criteria. So that's the. Okay. Now, if you. Yeah, okay, so the theorem that one has is that it's a Kobayashi-Hitchin type theorem. Is basically that data of E and rho for stable, for a stable E and rho determines monopole. So there's a bijective correspondence. So, theorem is that you want this monopoles. And remember, we specified the T's and the Lij are in bijective correspondence with the E and rho, where of course the Lij's appear in the singularity structure here, and of course the stability stable, and the TIs basically appear here. so the theorem is there in one-to-one correspondence. So I've given you this direction.
Rho is what, a flag or?
Rho is a map, a self-map of E to E, that is meromorphic. The singularities are the points pi, with the singular type, the zero Hori type, Lij. So that's all specified. You want the pi's there. And the monopoles, well, the points pi are also there. So I'm just saying this discrete data is living in both pictures, and the t's, you just see them in this stability.
Do you fix a t equals 0 slice? I mean,
Yeah.
so it will change if you change the slice?
No, everything's invariant in this sort of perverse way. That's what you should check. It's yeah. So it's actually an invariant notion. I mean, that's why I wrote out as an average degree, because you see it that way. Then there are explicit formulas where you sort of choose things. But it's okay. And the proof is well, in this way, it's just showing that it's stable, and that's fairly standard. And the going the other way is, well, the first thing is the row. You have to sort of build by hand parametrics for the monopole. So if you think about it, this map row basically tells you how to sort of move a bundle around here. So you sort of move it around and glue it back to the row. Then you have to, as you're sort of moving along here, you have to sort of insert a transition function that makes the holomorphic structure pop. And then you have to put in, basically by hand with a partition of unity, you sort of glue in some Dirac monopoles here. And you get something, in other words, because they're Dirac monopoles, actually satisfy the equation on a neighborhood of the point. And then, and so their curvature is actually sort of almost there in some sense. And the way to get there is to basically just apply Simpson. So Simpson basically was doing Higgs bundles with singularities along divisors, but if you look at his proof, basically, so you're looking on sigma cross S1, and you want it to be the anti-self-duality equation, so you add in an extra circle. And now your singularities are basically, instead of being at points, here they're along circles. And so the point is that singular set is very small. And you apply this Simpson heat flow technique, or Simpson-Donaldson heat flow. And sort of amusingly, because you start out with the Higgs field, this is with the Higgs field 0 case, which is, of course, the Simpson's Higgs field is a different Higgs field. But it still works. So you get a solution. On the thing, and then the last thing you have to check.
Sorry, so that shows that if you take the real moment map, it really takes the minimum on
Yeah.
the complex orbit.
So you're getting a solution. The only thing that Simpson doesn't give you, at least for the analytically inept like me, is the asymptotics here. But then you have this wonderful theorem that basically goes back to Peter Kronheimer's MSc thesis in Oxford. And he then had a student do a little bit more general version, which is what we actually use. So, and the idea roughly is that your Simpson flow locally, well, you're worried about the singularity of the point, so you're on a 3-ball across the circle, and you've got a singularity, which is the point across the circle. And this idea is basically you just take the Hopf vibration. And doing it this way, there's a way that you lift the Dirac monopoles from here to here. And this basically smooths them out. They become, all the singularity of the Dirac monopole basically lives in this vibration. And what you do basically now is you've got a 4-ball, and you already had the film, right? It's the Simpson film for heat flow on the whole thing. So you restrict the film to
Sorry, the film, what?
the heat flow,
The movie.
Oh,
the movie. You had the movie, right?
yeah.
And you watched it for all time,
Yeah, yeah, yeah.
and then when you got really bored, your monopole was fully cooked.
Mhm.
Okay, you still have the film, right?
Is that a Canadian word, film?
Sorry?
Is that a Canadian word, film?
Yeah, I don't think so. Okay, sorry.
As opposed
Movie?
to movie.
Whatever. These, but now you have the same thing, but you can replay it as a sort of boundary value problem. And now you already know that your initial conditions are smooth, so you just sort of follow it through. It's going to be smooth in infinity. So it stays a monopole once you sort of undo the Kronheimer thing and you have the right behavior. So that's that. Okay. There's a nice index calculation that Pauli does, and you can compute the dimension of the moduli. But maybe just another remark, which is that from E rho, you can take the spectral curve, which is determinant of rho z minus lambda times the identity equals 0, and sigma cross P1. And then you can lift E to sigma on across P1, so you get sort of pi star E.
Sorry, are you doing rank 2 or something?
Hmm?
Why
No,
is
no.
this?
Just a general,
Oh, lambda's at P1.
yeah.
Yeah, sorry.
So you take your
Yeah.
spectral curve, and you have to put in some twists here, but you basically look at the map rho z minus the identity on this thing, and you'll get something that lives on the spectral curve that is generically aligned one. So, and just the general sort of rules of this thing, basically you just take a direct image of this thing. Means that, so, follow spectral curve S. And, so this thing is actually encoded in L, and in fact, there was a talk last week where if you took sigma to be a torus, these things actually give you an integral system. So for an elliptic curve, an integral system. For higher genus, the symplectic form that you'd hope to get has some null directions, basically, so it doesn't. You can compute dimensions and things, and
So do the null directions depend on the poles of the variegative function?
yes. Offhand.
I mean, I'm just thinking these are group valued, and you've been lost
Yeah.
interest by the canonical
Well,
model. So
this is there's a good way of thinking of the metaphysics of this, which is that you're on a ruled surface, and if you classify so I'll just put points in so elements of the Hilbert scheme. Want to be more precise, but points in sigma across P1. And that's basically, you've got a spectral curve that's, bad picture, but sigma is P1. You've got a spectral curve that's sitting here. You represent your line bundle by a divisor in some generically good way. And the theorem that holds in a whole bunch of these integral systems is basically this map where you think of these points. Now you just erase the spectral curve and think of your point sitting in the surface. If the surface is Poisson, then it inherits a Poisson structure. Now, there's a funny thing that happens for all the Hitchin systems. You have the Poisson structure is considered.
It's symplectic outside the curve and then it becomes just a Poisson structure at the curve, or is it?
No, you've got an ambient Poisson structure on the surface. So just forget the curve, and now you have a bunch of points floating there. And if you tried hard enough, you could draw a curve through it, and generically unique.
What's the by degree of the curve?
Well, it's rank of the bundle here, and then something. I mean, it's the determinant bundle of that. So the point is that for the Hitchin systems, you're generally
rank in
Poisson
one direction,
structure.
presumably degree.
Sorry?
Rank of the bundle in one direction, degree of the bundle maybe in the other direction, is it? Maybe times.
not on my feet. For the Hitchin systems, the Poisson structures you end up considering over sigma have a sort of double zero on the surface and are singular for the generalized Hitchin system on fibers like this. But if sigma is either an elliptic curve or a P1, there's another Poisson structure that comes in, which has two zeros. And it's kind of amusing. You see the fibers here are C, and if you're considering endomorphism, then its eigenvalues naturally live in C. If you're considering an automorphism, its eigenvalues live in C star.
Is this Poisson structure generically full rank and?
Yeah.
It's a symplectic structure with some singularity somewhere, but.
Yeah, so there's a
Not just
classification of Poisson surfaces that you can look up. And basically there's a beautiful correspondence basically between Poisson surfaces and all the well-known sort of GLN integrable systems. And it's always by this sort of algorithm. I mean, it's not a theorem because I put in the words well known, but it's a remarkable correspondence anyway. Okay.
I'm sorry to belabor this point. Are we talking about a holomorphic symplectic structure here?
Yeah.
Or, oh, okay, so you just have a section.
It's a
Canonical-
holomorphic, it's a holomorphic integrable system, basically.
Okay,
These
okay.
curves
So
are
then
giving you.
you're gonna dimension
And the point is, I was just outlining the difference, and these are either Hitchin systems or Adler-Kosten, they have a long history, and these are the Spianen bracket systems, which are sort of group value things, and that's this case. But it sort of ceases to work when you go beyond elliptic curves. So now that I was sort of chatting about this with Imre Biswas, and yes, what happens when you consider arbitrary circle bundles? Okay. And so there you two x over sigma, the circle bundle. I'll just take it positive. And there the relevant geometry in 3 dimensions is the Sasakian geometry. So this is, in some senses, you can think of it as a regular. You put a connection on it that's sort of well chosen, and the connection form gives you a Sasakian structure. So one way of thinking of these Sasakian structures is the cone on X is scalar. So let's see what's the. So you start with a contact form with a connection form. alpha non-degenerate. One form, connection one form. And you could define on the cone a, so it's a contact form, so this is your curvature if you want. T star d alpha minus 2 r alpha wedge dr. That would be your Kähler form. Now, this is the Kähler one. So this is not the one you want. What you really want is omega tilde, which is d alpha. So you just divide by r squared, minus 2 alpha with dr over r. And this is not Kähler, but it's good to show.
Is there an R squared?
Yeah, it's an
R
R
squared
squared, it's
is
RT.
Oh, I forgot, sorry, r squared. No, apologies, I'm getting t's and r's.
No, no, you're good.
I'm okay?
Yeah.
Good. So you want this to be a good geometric, so using bar. Okay. And then for good geometrics, you have sort of similar stories.
Sorry, for the people who haven't heard all this, are you setting up what the geometry of X is?
I'm just setting up the geometry of X, I'm done now.
And what are the coordinates? What is R?
R is, I said, the one way of thinking of these, so you've got sigma here.
It's okay, the new manifold, X times R plus.
It's X.
It's X times R plus, so I
Cross section is all X.
The cross section is X.
In your picture,
Yeah,
you call it sigma X.
sorry, what did I call X?
Cone on X is
Yeah.
Kähler.
Yes.
Picture.
Ah, sorry, thank you.
So you're looking at
The
X
alphabet
times
is
R plus.
contracted. By the end of the talk, all letters will have the same meaning, which will simplify things greatly. My apologies. Okay.
Oh, so this is a way to set up a circle bundled over sigmas. So
Yeah, so I'm just saying you really want to think of the circle one.
But
You
you're setting up a metric structure on
Yeah.
this four-dimensional manifold and then slicing it at R equals 1.
Yeah. Now, the point is that this one works on, if you want, it works on X process one. So you have one in 4 dimensions, and you have a complex structure, and a one that has sort of nice properties, for which you still have this Kobayashi-Hitchin correspondence. And as a result, it goes way back to Nick Buchdahl, I think, the first one. So this, these long various generalizations.
So I guess a good prototype to keep in mind, although it's not directly relevant to what you're doing right now, if you just think about on a Hopf surface, there are sort of two interesting metrics, one which is the flat metric from C2, and then, but that wouldn't descend as a metric to the
Yeah.
quotient. So you therefore have to divide by radius squared so you get something that
Exactly.
is actually invariant under
But
relation.
then it's invariant out of it.
And then that's actually essentially.
So it's S3 cross S1 is the perfect example, and the fibers over, the S3 fibers over S2. Okay. Well, you just consider monopoles on this. On this. So same singularity. So what do I want to do? Again, if you want charges or degrees, Lij at the singular points, which I'll just call xi now. Okay. A bundle E.
So when you say monopoles on this it means X, right?
Yes. But minus again some xi. Good. You, that makes sense. Oh well. Still have a degree. Which is essentially a curvature interval, but now with this contact form. And you can show that these monopoles are, if you had a solution, well, again, the Hermite-Einstein, again, monopole equation, which would still be f minus star phi equals pi c times the identity times the lift on the form on the surface.
No, that's the alpha?
Yeah.
What makes it
Yeah.
the alpha?
So okay, and so you still have this. You can still do. Let's see now. What am I saying? So you can still do the. You can still scatter, but only locally.
What direction along the fiber?
As long as you've got a circle action. Okay. So now you get this sort of curious picture.
So by construction, your circle bundle has to be non-trivial, so you can't find a cross-section.
Exactly. So there's no choice of origin for your scattering. So you just choose some.
Where do you use the C1 as positive?
For this non-degeneracy of the metric, the d alpha. Okay. So, but now, your picture is as follows. You have your circle bundle, you have your base, you have the circle orbits, and they're sort of all traveling in one direction. Some singularities, like that. But now, of course, as Scott was remarking, there's no local section. So you just choose some open sets, alpha, and you take a section. Well, on U alpha, you can certainly then scatter all your way around. And so if you have let's call the image here D alpha. Okay, on U alpha, you get a bundle. E basically restricted to D alpha. And a map, rho alpha, from, so let's call this alpha. F is used already.
Wait, alpha's now labeling patches and not as, it's not the connection anymore. Alpha's now labeling patches.
Oh, no, this is
J, or
J,
is that
okay, this is really going to cause acute mental stress, you realize, because I will now have to translate all my Greek indices into Latin. And
EJ. Keeping the fixing.
okay, so you get a bundle, right? EJ to EJ. If there's a sort of singularity that's in the way, you get the same singular structures. So you get the same sort of data. And now, of course, if you're taking another section, which used to be called U beta, which is now called UI, but I use, so maybe K. K? K. Okay. Let's be extravagant. It's near the end of the talk anyway. Okay, you'll get rho K, EK to EK, and you'll get a scattering map. So you just go along here to there, and you'll get a rho. Let's see, how do I want to compose it? I suppose I'm going to get rho K J want them to sort of look, when I start composing them, I want them to sort of look
Presumably.
cocyclic. So I put the K first and then the K. Okay.
The bundle's oriented, so you know which way to go. The bundle's
The circle
oriented,
bundle,
so
yeah,
you
it's
know
a
which way
circle
to go.
That's exactly the point, is you've just got one way to go, which is positive, because it's a circle action. So that action is telling you which way to go.
Oh, okay.
Okay? But now, you look at the cocycle. Right, and what are you getting? You're getting rho jk, rho kj, if I've done this correctly, should be equal to rho j. Because I start here, and then I'm going here, I can't go back, I have to go round.
Oh,
And I come back. So it's not that it's equal to the identity, it's got this twist in it. So these are sort of have this gerb-like flavor,
So, rho J is,
gerb-like things.
rho J is
He's
holomorphic.
Rho J is holomorphic,
He's chosen this so that you're avoiding the,
Yeah.
Yeah, yeah.
or meromorphic, I mean, it doesn't matter.
The rho JKs are.
They're just transport from here to here.
They're no, which is.
he's avoided the puncture, so it's.
I could go through them and they'd have a single area.
Okay, sorry.
Everything's meromorphic. He's sort of.
Yeah, the rho J's are meromorphic, the rho KJs are holomorphic. No, no.
Yeah, if they could be holomorphic, they could be meromorphic.
If rho J
But he's chosen it so the overlaps of charts
Yeah,
don't.
I could, but I generally one tries to.
Wait a second, the rho JKs in general are meromorphic, right?
They could be, if there was a pole in the way.
And the road J's would be too.
And then the road J's, everybody would be meromorphic and, they're all together. But you could also arrange for them to be holomorphic by just choosing your covering length. Okay, and then, triple overlaps, well, rho K, J, I don't know, rho K, L, rho L, J. Well, that really depends on whether the things occur in order or not. So you'll get KL is equal to rho JL or rho JL rho L, right? So depending on whether they occur in cyclic order or not. That's the type of thing you get. And so it's like, has this sort of slightly sort of twisty gerb-like property. And so they still have spectral curves. Right, rho alpha is conjugate to rho beta. So rho alpha is going around this way, rho beta is going from here, or rho j into k. Okay, so to go from here to here, I could go around this way and come back, basically. So it's basically they're conjugates. Okay, so they have the same spectrum. So still, determinant of rho j minus lambda plus the identity equals 0. It's independent of j.
What's that? Rho J was only conjugate to rho K on the overlap, UJ
Yeah.
UK, but then this is globally defined, right?
This is globally defined. They paste together nicely. Okay, and what happens when you take and then compare this with the same thing with k. What you get is one of these gerb-like things, not for UN, but for U1, or GLN, but for GL1. So, sorry? They are gerbs.
A line gerb.
A line gerb. I sent a note to Michael Murray, who's worked both on monopoles and gerbs. I said, what do you call these things? I never got an answer, so it's prose of some sort. And rank 1 gerb-like thing. Now, if you actually try to build one of these gerb-like things, now you notice what happens is in rank 1, row K is equal to row L, because they're congruent. And so what you've got is basically a function that's coming in to twist a cocycle. And so you fix a function now, and you can build one explicitly. Basically, you just trivialize your bundle on the complement of some points, and you can just build a cocycle by hand, basically, that has the requisite properties. And what you see, basically, is you've got an equation that's what? Rho alpha beta, rho beta alpha is rho. And if I twist this by sigma alpha beta alpha equals 1, in other words, if I take the transition functions for a line bundle, I get just add these in, I get the same equation. And so basically you're seeing that in rank 1, one of these GLTs for rho are just basically an affine copy of the Jacobian, of the Picard variety. So it's a torsor.
Why does it have to be pick zero?
It doesn't have to be big.
That's the one that's
So
Right, it has to be peak zero, otherwise it's a group.
Is it connected? I mean,
well, you could, except probably you'll get degree
It's a
considerations.
group, but I mean, many components are maybe on some of the ones.
But in any case, you're seeing basically the same structure that came in the sigma cross T1 base. So it's saying basically these moduli spaces should look, oh, you're right, fairly similar. All this is very fine. What you're missing here is the theorem that says that if I give you one of these pieces of data, you've got the thing that goes back. Now you have Bookdahl's theorem that works for Gaudichon without singularities. You've got Simpson's theorem that works for the Kähler with singularities, and these are very mild compared to a lot of other things that have been considered. So I guess it's probably true.
What periodicity condition would you put on the R?
We asked Telemann, we got a very interesting problem. So
So when you want to be using Bookdahl on a complex surface, so you have to make R logarithmically periodic, right? The radial direction you want to mod out by some number to.
oh no, you just take the same. You'd have just sigma x cross a circle.
Yeah,
That's your Gaudichon manifold. You have singularities, Dirac singularities.
But what I'm saying is that you actually have a family of different complex structures depending upon how long the S1 is. I mean, you've got this.
Yeah. Oh sure, yeah. Well, you just take. I mean, this is fine.
Does it matter when you roll it up?
Yeah, it'll matter for the stability because they're
it'll change.
the stability. Well, the stability basically there's. I said there was a curvature integral. Again, you can't work it out in particular, but if you shift the TIs along a circle orbit, you get basically sort of the same formula you get in the S1 cross sigma case for the variation. So it's all sort of an affine shift of that, somehow, of that sigma cross S1. And anyway, so anyway, all I was saying is one suspects that it's true. Again, we asked somebody else who said there were issues about the Donaldson functional one that's used to sort of control the heat flow when you try to apply Simpson's arguments. But still, it's sort of this intriguing thing that's coming up in a fairly natural situation that's sort of still there and is basically, you see, you're getting, at least the parameter count is very similar to the case that's solved, which is this one across. That's fine. Yeah, thank you very much.
Questions?
What can you say about the moduli space of the monopoles on sigma times S1?
Well, you can, like I said, there's for the torus, when sigma is an elliptic curve, we have a rather long paper for the Hamiltonian, which does a lot of the Hamiltonian geometry. Actually, Pauli has a very nice index calculation, gives at least the dimension, which coincides with something G plus 1
It's a lot of local terms.
plus sum over I, sum over. I'll suppose the Lij's are ordered in a suitable way, something like Li J prime minus Lij. There are two. No, I think that's it.
You take the anti-dominant weight in the
Yeah.
vowel chamber and you
Yeah.
have the local term.
So there you go.
So, right, so I know the dimension, but, I mean, let's see, it's not hyperkiller anymore, right? In general.
No one does. Yeah.
Maybe
For
hypermedia.
the elliptic curve?
For the elliptic curve, it would
It will
be.
be, yeah.
And the trivial one,
Sorry.
and when you take the product.
Yeah. For the trivial case, yeah.
But I mean, is it non-compact? I mean, you're not a compact three manifolds.
Yeah, well, I mean, as soon as you have a stability.
But does that mean there's some
Issue.
Kodaira surface that naturally comes in, and it's sort of related to this question I was asking before. I mean, if you're working with an elliptic curve, and then you look at you now look at your x corresponding to a choice of bundle, and then you multiply by a circle, you'll get a Kodaira surface.
Yeah.
But which circle you multiply, you actually have sort of one real parameter family of
Yeah,
Kodaira
sure.
surfaces that are. Does he ever use the Kodaira surface in his arguments, or?
For.
In making these kinds of calculations, you're saying Pauli had very.
No, it was just a straight index calculation on using a sort of an,
I see, there's no analysis of the
It's
actual
like the
moduli.
Colias index thing. I mean, you can.
So if you start with Sasaki Einstein, you still should get some nice.
Well, this one's, it's not, that's not Sasaki Einstein, I mean, it's Sasaki, but it's not Sasaki.
It cannot be Sasaki Einstein.
Yeah, so I mean, it's related to the geometry of the Heisenberg group, and.
I have no idea what you get.
You take the elliptic curve and put Dirac singularities at all the half period points. So this is a kind of Cooper approximation, I presume.
Oh, jeez.
Right? So you have the 2 to the 8 singularities.
Yeah.
But all your LIs that are the same or half
Yeah.
or something, maybe it's a rather special.
Maybe that might be something.
nice space.
I don't know if it blows up the mod 2 quotient.
Well, so what is it? I mean, we know what kind of singularity to put it at points for monopoles. It has to be a direct singularity.
Yeah.
For instantons, it's not so clear, but maybe there's some kind of approximation to K3, which is better than the ALG ones. Well, I don't know, maybe Stoke.
You mean K3 as
He's
a modulus?
gone.
I have no idea.
Anyway, adjusting those positions.
Yeah.
I mean, not generic, of course.
Yeah.
Something special is going to happen.
No, that's a very good point.
Is there any way of?
I mean, you're certainly getting symplectic, holomorphic symplectic things.
Is there any way of arriving at a Dirac type monopole without putting it in by hand, if you put in some weaker conditions? You just know something about the behavior of the curvature and the puncture and.
this sort of four-ball thing.
I mean, sort of, you have some model which is actually a sum of line bundles, but then you have some error term that mixes them.
Yeah, there's.
And just, if you're trying to show that asymptotic as you approach, that somehow the connection breaks up in such a way, what do you have to impose? What's the like geometric condition?
Sorry, I'm still thinking about this moduli space. Is there a description of it in terms of the moduli space of holomorphic maps? I mean, you almost have it with this row, right? This meromorphic.
Well, that is the holomorphic data, the bundle E in row, but the
It's
bundle's
just
there.
E in row, it's not, yeah, okay, it's in.
So
it's
for
a
example,
meromorphic.
if.
Okay, it's a meromorphic
Yeah,
holomorphism.
if you had a
Okay.
you know, P1,
Yeah.
you'd be in business for small. But the Hamiltonian structure is very differently the group value Scianon bracket that's involved as opposed to the.
So in this case,
Well, but P1 also, it's just,
So for P1, you need to presumably you need to be able to bound the Grothendieck-Birkhoff decomposition using stability somehow, I guess. I mean, this is some finite dimensional moduli space.
Yeah,
Bundle E is going to be a sum of line bundles.
Yeah.
Your meromorphic function then splits up into lots of pieces. You describe that
Yeah.
very. But stability.
But stability is generic, as soon as you have a smooth spectral curve.
Yeah, but I'm thinking of the full picture.
Yeah.
The full moduli space. Maybe you could describe it. I mean, but you say it is already described for P1.
Well, I mean, P1, we've got meromorphic maps on the open set that would correspond to the trivial bundle.
Yeah.
And it's just, a meromorphic map.
Yeah, but I'm thinking of filling in the extra pieces.
Yeah, of course, yes. Then you'd expect that the stability would impose some bounds, because that'll come in this T degree.
Shouldn't it have a compactification? I mean, the obvious asymptotic regions are no longer there. And maybe monopoles can be absorbed and emitted at the singular points, so maybe there's some interesting bubbling. But I would think that this moduli space has a compactification. Because the monopoles can't get far apart.
They can't get too close together either because they have a size, don't they? And they don't bubble.
Yeah, they sort of, you can imagine it hits the Dirac.
No, sure,
I don't know
that's a
what
kind
happens
of
to
bubbling phenomenon. They could get absorbed in these, the Tuft singularity.
They only have finite size if you fix the asymptotic Higgs field. And here there is no
Right.
asymptotic fixed Higgs field.
Okay, yeah, that's true.
Can you throw in a twist on the base? I mean, at the moment you have just a product of C1 cos S1. You could take.
You can do some equivariant things.
well, at the end, he's actually looking at it's a non-trivial circle bundle for this second.
A non-trivial circle bundle, but the case, for example, I mean, if you had sort of a finite group actions, then everything just generalizes. You can put in some equivariance and things go well. But you can have flat circle bundles that don't have any, that aren't somehow quotients of things like here.
This might be related to what you just said. But, these regular Sasaki manifolds, they have a circle action. I think there's some interest in instantons on monopoles on irregular Sasaki manifolds. Have you thought about that before?
I'll give it to a student. I have no idea. Of course,
I mean, it's
should
a circle action, it's not a circle action, it's only an action.
Yeah, no, I mean, I have no idea. I mean, it's the same thing in some ways with the